I'm happy to be back. Um, and today I'm going to be presenting on a very interesting topic, subsea systems. Uh, it's something which not everybody is very familiar about. People always hear about offshore oil and gas production, but nobody, or a very less amount of people actually have an idea about the quantum of infrastructure and the engineering that actually goes in production of this oil and gas offshore. So I will try to get an appreciation for get people to appreciate that how big of a infrastructure, how much effort, how much engineering goes in developing all of those offshore oil and gas production platforms. So without any further ado, subsea production systems, somebody might ask what it is. Essentially, this is just a collection of equipment, technology that is used to extract, transport, and distribute hydrocarbons, oil and gas, from your subsea reserves. Subsea production systems are very customized. They depend upon the client, they depend upon the reservoir requirements, how big the reservoir is, how much spread it is, and how much you have to drill. Some of the installed subsea equipment include production trees, manifolds, subsea pumps, subsea compression, compressors, wellheads, flow lines. The extracted hydrocarbon, whatever you will drill and you will get out of these wells, will be either transported through a subsea pipeline to an onshore facility, or it will be transported through tankers to a facility where it will be able to be processed onshore. So when we talk about subsea production systems, this is all we are going to talk about today. I'm going to talk to you system by system, subsystem by system, that what a subsea production facility essentially looks like. So what you can see over here is your subsea infrastructure. All of it is actually lying on the seabed. So 100 meters, 200 meters on the seabed, which is connected through a series of pipelines, cables, and risers through a drill ship. So what you see over the top over here, it is drill ship, or it can be replaced by what we call a FPSO, which is floating production storage unit. So there are some terminologies that we will use. Don't get confused by these terminologies. I will explain them as we go along. But essentially, this is what your subsea infrastructure would look like. All of it is actually lying on the seabed. Some of it is permanent, some of it can be removed. So the critical part of the subsea infrastructure is essentially what we call a subsea tree. If you see this picture over here, I want you to concentrate right over here. This is what we call a subsea tree. This is a permanent part of this subsea infrastructure, and it is one of the first things that we install when we are drilling a well subsea. So this is also called a Christmas tree. Whatever we are going to talk about, the components that we are going to talk about in offshore industry, they are also present in some form or another in onshore as well. So when we say Christmas tree, this is also present onshore. That means on the land. But the subsea tree is a little bit more complicated. What you see over here is what we call a horizontal tree. And one of the things that you will notice is all of these small little terminations or terminal blocks which you see over here. These are essentially your ROV connections. ROV is remotely operated vehicle. This is like a small little vehicle that goes from your drill ship all the way to the bottom, to the sea. And then this remotely operated vehicle has these arms that it can use to manipulate these connections. So you have to close a valve, open a valve, or to control something. The ROV can go and it can actually interact with this junction box right over here, and it can manipulate the valve. As I mentioned, there are two types of trees, the horizontal tree and a vertical tree. Horizontal tree is what you see over here. The horizontal tree is more preferred because it saves the space, like it's not that much tall, it is more wider. So it actually saves you the vertical space. because when we'll go further in the presentation, you will see that they are on top of the subsea tree. There are other subsystems that go on top of this. So the stack up height is very the subsea tree has a complex set of valves to control the flow of hydrocarbons that are coming from the well into the flow lines. It allows for a safe and optimum extraction of oil and gas. It's a permanent subsea structure, which is installed as a part of a completion of the well and stays usually on the subsea bed along the whole life of the well. The size of the subsea tree essentially matters on how big your reservoir or how much flow you are getting and how much pressure you are getting, as well as the temperature. The next thing which you see over here, I'm going to point you to this direction. We talked about subsea tree. The next thing which this tree is connected to through this jumper line is called a subsea manifold. Now, what is subsea manifold? Subsea manifold is essentially a junction. All of your subsea trees are connected through jumper lines to this subsea manifold. This is where all of the hydrocarbons are mixed together that are coming from different wells, and then they are transported to the pipeline. The trees are connected to the manifold through this jumper right over here. You can see over here. The tree is over here, the manifold is right over here, and they are connected to each other. It is also a subsea permanent structure, and it stays on the seabed throughout the entire life cycle of it. Okay. The oil and gas, once it leaves the tree, it is transported through this jumper cable, comes to this manifold, and from this manifold, it is connected to the pipeline where it can be taken either offshore to a FPSO vessel, which is floating production and storage offloading vessel, or it can be transported through subsea pipelines to onshore processing facility. Subsea pump. As you guys know that sometimes the fluid that we extract from the well, whether it's a water well, whether it's oil and gas well, sometimes it does not have enough energy to pump itself all the way to the surface because we are 200 to 300 meters from the sea or the surface of the sea. So to cover all that distance, you need some sort of energy to pump it from the seabed to the sea level. For that, we actually use something which is called a subsea pump. So subsea pump will impart the necessary head to the fluid so that it can go to the floating production of storage offshore vessels. It is also a permanent structure that is used to boost the flow of hydrocarbons from reservoir to the production facilities, whether those production facilities are on the sea level or they are onshore in an onshore processing facility. The pumping station, sometimes the pumping station is kind of an optional module. Sometimes you have enough flow of the hydrocarbons, so you don't need subsea pump. But if you don't have enough flow of the hydrocarbons, then you need a subsea pump to provide that boost. Wellhead. The wellhead is one of the most essential and safety critical part of any well, whether it's onshore or offshore. It's a pressure containing system, and it is designed according to regulatory requirements as well as the API requirements. API is American Petroleum Institute. They come up with certain standards that determine how the wellhead should be designed. And this is based on numbers of years of experience that have been gained and disasters that have been encountered by mankind in the previous years. So there are very stringent requirements on which the companies actually designed the wellhead. The wellhead is the last piece of the completion on top of which the tree is actually installed. So it's a pressure containing system that is installed on the seafloor to provide support for the tree. So you already saw the subsea tree. The subsea tree is actually sitting on top of a wellhead. And it provides the support for the tree. It also provides the pressure seal for the wellbore. So it essentially prevents the wellbore fluid from going into the sea. So it's a sealing component. It also acts as an interface between the Christmas tree and BOP with the formation. It's a permanent structure as well. It is part of the completion of the well. It is there for the entire life cycle of the well. and it is one of the most critical systems which stays there for drilling as well as for the completion operation. So when you are drilling the well, it stays over there. When you are completing or when you are producing the well, it still stays over there as well. And apart from providing the sealing, it environmental sealing, it also have one critical feature, which is it supports the casing. So casing is essentially a tubing that goes downhole for you to present for you to produce. Think of it as like a straw. So that straw is actually producing wellbore fluid all the way to the surface. So that straw is being supported by the wellhead. It is resting, all the weight of that straw is actually resting on this wellhead. Subsea completion string. So we talked about the wellhead. The wellhead is right over here at the top, which you can see over here. On top of the wellhead, as I mentioned, that there is a subsea tree. The wellhead is supporting the weight of the subsea tree, and then all that production string is hanging from this wellhead. So the selection of the tubulars and tools, equipment located in the individual wellbore depends upon how deep your well is, how much flow it is producing, how much pressure it is producing. It is a direct passageway from the formation to the surface, and it is usually placed inside the conductor or casing string. There are a few major components of this casing string, which you see right over here. These components make sure that you produce the wellbore fluid safely and securely. One of these is called subsurface safety valve. As the name suggests, it's a safety valve. It is meant to turn off the flow if there is any emergency, either on the seabed or on the top side. So you can use that subsurface safety valve and it will stop any production of, it is usually at the very bottom of the well. And once you turn it on or turn it off, you can actually start or stop your production. Then there are other things like formation isolation valve. Formation isolation valve is also like a safety valve, but as the name suggests, you can have multiple formations which are part of the wellbore, right? What this formation isolation valve does is that it can essentially turn off one formation and let other formations produce. Right. And then your tubing hanger. Tubing hanger is also like type of a straw. It is the smallest tubing that is in the well, and it is also called production tubing, through which the wellbore fluids are flowing from the bottom all the way to the top. Blowout preventer. You probably might have heard about this. This is also a very critical, safety critical component. It is usually used when we are drilling the well. And blowout preventer has a series of rams and valves that it can open and close in case there is efficiency. For example, there is a sudden influx of wellbore fluid at a very high pressure and very high flow rate that you need to terminate or you need to isolate the wellbore. Then BOP acts like a safety device to cut off that production. You can see some of the components of there are like pipe isolation valves, casing rams that you can use to isolate that tubing. And in the worst case scenario, you can actually cut that tubing and it will isolate the wellbore at the BOP. This BOP is usually on top of the subsea wellhead. As I mentioned earlier, that subsea wellhead, you are like constrained on the space. You want it to be as short as possible so that you can have rest of the systems on top of the subsea wellhead. So you can see rest of the systems right over here. You have your BOP stack, and then on top of the BOP stack, you have your lower marine riser package. I'm going to talk about lower marine riser package in the next slide. But what you want is that your BOP, it has to be serviced, it has to be maintained at proper intervals because it is a safety critical device. It is able to contain the wellbore pressure using rams in case of breakout or testing. Lower marine riser package. This is like a termination assembly. What it helps you to do is that if there is a storm on the top side where your rig is station, if there's a storm and there's a lot of movement of the rig, and you are unable to dynamically control it, and you feel that, or the operator feel that it is becoming too much, the movement, then what they can do is that they can actually terminate the entire string. You can see the riser over here. They can disconnect right over here at LMRP, and they can reposition the rig and come back another day to connect with it. So essentially, it is your termination. It is installed to allow for emergency disconnect feature. It is also consists of different type of RAMs, shear RAMs, annular RAMs, as well. So your BOP and your LMRP are essentially your safety critical components in your offshore oil and gas exploration. So deep water operation, there are different types of, we are going to talk about different type of rigs that are used in offshore. Not one rig fit all sizes. So you have different type of rigs, you have different type of drill ships that are required for different depths of operations and how bad the seas are. In the water depths that are deeper than 100 meters, drilling and completion operation are usually conducted using floating vessels such as semi-submersible, which you can see right over here, and drill ships, which you can see right over here at the top right corner, which can be anchored. So they can be anchored to the seafloor, or they can be unanchored. In case of unanchored, you can see right over here, the drill ship is not anchored to the seafloor. How it maintains its position is called dynamic reposition. It has a series of impellers around the ship, which move based on the position of the ship, and they can actually dynamically position it. So on the floating vessels, all the equipment is in a constant motion relative to the datum point, that is your seabed. Because your seabed is your fixed point, everything is relatively have a motion in relative to it. For the floating operations, the ability to contain, shear, and disconnect from the wellbore is a critical feature, as I mentioned earlier, to ensure the safe operation. So you want your equipment to be flexible enough so that you can terminate in case of storm and you can come back. Your subsea infrastructure, all of it is connected through something which is called riser. Riser is a pipe that is connected. It's a very flexible pipe. One thing. It is connected from your lower marine riser package all the way to your drill ship. It provides for the passage of the completion string, so it has to be big enough so that all the tools, all the logging tools, all the drilling tools, drill bit can actually pass through that riser package. And it has to be flexible enough so it can compensate for any relative motion between the vessel and the seabed. So these are some of the components. You can see a subsea development. You can see how vast it is, how big it is, and a lot of it is actually sitting on the seabed. So one thing which you can see, a cluster of wells over here. This is essentially called a drill center. Your production risers are right over here. The production risers, as I mentioned, is a series of pipes that are connected between seabed and your drill ship or your FPSO. This is your FPSO right over here at the top. And then your flow lines and control umbilicals. Flow lines and control umbilicals. Flow lines are where your oil and gas are actually flowing, and control umbilicals is where your hydraulic and electrical lines are. These hydraulic and electrical lines are required for controlling the subsea trees and subsea control modules. So this illustration is a very good example of a subsea production system. It's a conceptual layout just for you to appreciate how big and vast it is and how the field is usually laid out. It is very extensive field with multiple drill centers. You can see multiple drill centers right over here. There is a drill center right over here. There is a drill center right over here. Some of the main components which you have already seen are production risers, FPSO, flow line, and control umbilicals. Now, one thing which you can see right over here as well, that there is a production buoy right over here. So in some of the cases when you are very far out in the ocean, you cannot lay down the subsea production lines from the FPSO all the way to the onshore processing facilities. In that case, you put production buoy, the tankers can come attached to this production buoy, take the oil and gas and take it up to the onshore facility or wherever it is going to be processed. So this is what we call a drill center. We talked about the drill center in the previous slide where you saw it right over here. I'm going to zoom on it. I'm going to talk about some of the components of this drill center. So this drill center illustrates a typical arrangement that includes flow line and termination, or FLET, and pipeline. Sometimes it is also called a pipeline and termination, which you can see right over here. This pipeline and termination is, these are your subsea trees. These are connected to the manifold. This manifold is actually connected through a jumper to a PLET. PLET is actually a system on which your pipeline will come and attach. So you can see the pipeline comes over here and it terminates over here. Then there is something which is called a subsea distribution unit, SDU. This SDU you can see right over here. SDU essentially acts like a junction box. This is where your master hydraulic and electrical line will come and connect. And from here, it distributes the electrical lines to different trees and manifolds. So it acts like a distribution unit. All of this, the SDUs, the PLETs, and the subsea trees, all of this equipment is clustered around the manifold. You can see the manifold right over here. All of these things are centered around the manifold, so that if the drill ship is moved and located over the drill center, the drill ship is able to move around and access all of the different subsea wells and trees. The jumpers connect the subsea trees to the manifold where the flow is commingled. So essentially the flow that is coming from the subsea tree is commingled into this manifold, and from this manifold it goes through a jumper line to the PLET, and from PLET it is transported to the pipeline. So this is essentially what you call a drill center. So let's talk about how the basic subsea production works. This is a satellite well or a single well tieback. That means we're going to talk about one well. And then once we talk about one well, then we are going to extrapolate that concept into multiple wells and cluster production as well. So this animation shows the installation of the basic subsea production system with a satellite or single well tieback configuration. First, the well is drilled through the sea, floor into the reservoir. The subsea tree is then installed on top of this well, the wellhead. The host facility, which you can see right over here, is also installed. This host facility can be floating, or this could be standing on the sea floor. That depends upon how deep your sea or ocean is over there. And it is either standing or floating, which is followed by umbilicals and production flow lines between the trees and the host facility. The export line with a large bore is there to accommodate multiple well tiebacks. So your export line over here, it is usually a very high very big diameter pipeline. That is to make sure that if there are multiple wells, then it can accommodate the flow from those multiple wells. This is a very typical setup that works in places like Louisiana, Mississippi, or Texas, where the pipeline can go up to the shore. As I previously discussed, in the areas such as West Africa, the host facility might be standing alone without interconnection to the beach or any surface or the onshore facility. In that case, a shuttle tanker will come, attach itself to the buoy, and take oil to the market. The graphic that I'm using is very simple, and this is there for you to understand the concept of the subsea production. This is a single well tieback. Usually, in the production, in the exploration that we are seeing now, single well tieback is very hard to come by. Usually, you have multiple well tieback. As I mentioned earlier, this is that straw that acts like, this is production tubing or casing, acts like that straw that takes the production from the reservoir all the way to the surface. And on the surface of the seabed, you have your wellhead and then there will be a tree on top of it. This is, I'm going to talk about a subsea tree and compare it with a subsea mudline tree. So subsea mudline tree is used for uh, shallow water production, and a subsea tree is used for deep water production. To install this kind of a mudline tree, this is a mudline tree because it is essentially not at the seabed. This subsea tree is essentially on the sea, like where your drill ship is, and it is connected through the series of pipe all the way to the downhole. While it can be used, it can be installed using divers. While in this case, which is a typical subsea tree, this is installed on the seabed. It is right on the seabed, and it is diverless. That means the diver cannot dive all the way to the typical subsea tree. So you need to have remotely operated vehicles uh, that you can use to open and close the valve. Now, remember I talked about that no size fits all, so no single type of a platform or a subsea production platform can be used for all of the types of production. So this actually shows you the difference between all of them. I'm going to start from the very left. This is what we call a deep water platform. What you can see is it is resting on the seabed. Then these are compliant towers. These are also resting on the seabed. You have TLP, which is tension leg platform, and then your spar concept. But from here, you can see right over here that from spar onwards, they are not resting on the seabed. They can be anchored to the seabed, but they are not resting on the seabed. So your FPU, the floating production unit, and your tension leg platforms are essentially tension leg platform is dynamically positioned. FPU is usually anchored to the seabed. And then your FPSO and your drill ships are essentially dynamically positioned where they don't have any anchor to the seabed. So in case of your mudline tree, your mudline tree would be right here on the platform, and it is connected through the pipe all the way to the surface. But in case of your subsea tree would be right here on the seabed. So this is essentially we talked about the electrical and hydraulic lines. The electrical and hydraulic lines they are running between the tree and the host facilities. They are used to control the tree, so you can manipulate your flow. And the electrical and hydraulic control lines allow for remote operation of the tree to make sure that you don't have to have a ROV there at all times. The control lines open the valves, close the valves, allow the production fluid to flow from the wellhead through the tree and to be distributed through the pipeline. The pipeline provides a means for producing the fluid back to the host facility from where it can be processed. That means the water, oil, and gas will be separated. So the water can be used to be injected back into the reservoir, or it can be disposed of. The oil will be processed and it will be transported through the pipeline, and the gas can be either transported through the pipeline or it can be flared right there at the host facility. So we talked about the single well tieback. Now let's talk about this multiple well tieback. So multiple well tieback, you have probably seen this in the earlier pictures as well. You have your manifold right over here, and this is well number 1, well number 2, well number 3, and well number 4. All of this is connected through a 4 template manifold right over here. SDU is essentially your junction box from where your electrical and hydraulic control lines are getting distributed. So master line comes over here, and from here it gets distributed to each individual tree. These electrical and hydraulic lines are also called EFL or HFL, electrical flying leads, hydraulic flying leads. So whenever I'm talking about EFL, I'm talking about the electrical line. HFL would be the hydraulic line. So this illustration uses multiple well tieback configuration to show how EFLs and HFLs are connected to the subsea trees and manifolds, and they connect the subsea trees and manifolds to the SDU of subsea distribution unit within the drill center. Multiple well tiebacks are simply multiple wells tied together by production manifolds. The HFLs and EFLs, they are all laid out on the seabed. So they are resting on the seabed. Generally, they are very flexible and they are installed using ROVs. All the efforts are made to make sure that they don't crisscross each other, because when they crisscross each other, it makes the maintenance very difficult. Because if you have to, let's say, if there is an electrical fault or a hydraulic issue, and you need to pull these or uninstall or dismantle these electrical flying leads or hydraulic flying leads, if they are crisscrossing on each other, it becomes very difficult. So we make all the efforts to make sure that they are not crossing each other. Now, what physically these HFLs and EFLs actually look like, this is what we call a HFL, hydraulic flying lead. And you can see how big it is, and it is actually wrapped on a spool. This shows a worker that is engaged in the process of loading a HFL onto the deployment frame, which will then be lowered onto the steep load. This installation frame has mud mats at the very bottom. You can see the mud mats at the very bottom, or mud plates, which prevents it from sinking into the mud. So the mud mats actually work like the same way as a snowshoe, which prevents you from sinking into the snow. The deployment frame allows the ROV to come, pick the leads and off this frame and fly them onto the place wherever they are hooking up. One end will be hooked up to the object being controlled, and the other end will be hooked up to the object that has the control. One end will be attached to your SDU, and because SDU is actually controlling it, and the other end will be attached to your either manifold or your tree. This is what you can see the HFL already installed with a subsea tree. It shows the HFL stab onto a subsea tree. The ROV engages it and flies it over it right over here. So you can see it on the surface, but this is installed on the surface. But if you have to install it in the subsea environment, then the ROV will come. The ROV will take this HFL and it will stab it into this subsea tree. It has a locking mechanism or a thread to make sure that it does not disconnect. But there are three other small lines which you will see over here. These are called EFLs, electrical flying leads. EFLs compared to HFLs are much more flexible. They are smaller in diameter as well. Think of it, EFLs as similar to extension cord. They have electrical plugs at the end that are made up or connected under the sea. Now, this is a typical hydraulic flying lead with the ROV stab plate connected to the tree. So this is, so the ROV will come, attach over here, and then it will push or stab this HFL into this tree. So one of the things which I didn't talk about is what we call jumpers that are used in the drill center. The jumpers that are shown over here are called well jumpers. The well jumpers connect the subsea tree to the production manifolds. The production jumpers are used to transport flow from manifold to the flow and termination line. So these are called well jumpers because these are connected from, so these are called well jumpers because they are connected from subsea tree to your manifold. And this one is called your production jumper, which is because it is connected from your manifold to your PLET or FLET. You can see the quantum of the size of these typical subsea jumpers. They are huge. You can see a person which is standing right over here. You can see a huge piece of tubular that can be used to connect the manifold to the tree or manifold to the PLET. This is the jumper being transported. Now, typical field layouts, we talked about satellite well, which is one well by itself, but you can have different other configurations as well. You can have daisy chains, which are wells, which are connected in series to each other. You can have clusters, which are group of wells, which are connected or surrounded around a single manifold. And then you can have a template. A template is a series of these wells, which are very closely spaced around each other. So this is a multiple well tieback scenario. We talked about it earlier as well. But this is an actual subsea tieback. You can see you have subsea trees right over here. and then they are connected through jumpers to a manifold. So the jumper is right over here. It is connected with a manifold. And then there are HFL and EFL, which are connected through the SDU. Your SDU is right over here. So HFLs and EFLs, you can see them with a dotted line connected to your subsea tree. And from your subsea tree, you can see a solid line which represents a jumper connected to the manifold. So this is shows interconnected jumper, what we called a daisy chain. You can see right over here, interconnected jumpers between two manifolds. This is called a daisy chain configuration. Once you have your pipelines installed, you will have your manifold installed and you have trees and manifolds. What you do is that you essentially take a pigging loop out of one of the manifolds, and once you take it off, you connect a jumper between the two manifolds. So these two are essentially connected in series with each other. So that's why it's called daisy chain. This is typical six-well manifold. This is going to be daisy chain, so that means there will be one more manifold like that on the side over here once it is installed, and you will have two jumpers running between this and this connected to the manifold on the right hand side. This is a 4-well manifold. You can see right over here, and this is what we call a pigging loop. So you can have a 4-well manifold, you can have a 6-well manifold, and so on and so forth. We talked about the flow and termination line. This is a very simple piece of equipment. This is where your pipeline that is taking the flow all the way to the onshore facility will come and attach. Let's talk a little bit about the SDU, or subsea distribution unit. This SDU has something which is called UTA, or umbilical termination assembly. This is where your electrical and hydraulic lines will come and attach. This is your umbilical. You can see these are your electrical lines. You can see how many conductors are there, and they are doing multiple purposes. You have your telemetry lines, which are taking your control signals. You have your electrical lines, which are essentially taking your electrical lines. So you can see right over here, umbilical is quite huge. It is very large in diameter, and it can have your electrical lines and hydraulic lines all bunched together, and then they are attached with the UTA right over here. This will give you an appreciation of how the umbilicals are actually installed. It shows umbilical on an installation wheel, which is prior to the transportation offshore. It is a good example of a relative size of umbilical. So with this, I would like to conclude my presentation. Offshore oil and gas, I want to mention one thing, accounts for 30% of the world's oil and gas production. So there's a significant chunk of our energy needs that are fulfilled by the subsea oil and gas. They play a very critical role. They are actually essentially a backbone of the oil and gas production. In that, subsea systems are backbone of the oil and gas production systems to ensure reliable, safe operation and efficient extraction through these deep and ultra deep water depths. They represent a marvel of technological innovation with advancement in robotics, remote monitoring, and material sciences. We are using premium materials, high pressure systems, high pressure piping, along with ROVs and robotics to install and operate these subsea systems. And all of this is to ensure reliable, enhanced, and reliable production with reduced costs over a long period of time. So these production systems are producing for decades reliably. So the technological advancements is very important to make that happen. And then finally, with the increase in the world's population and the demand of energy increasing, the E&P companies and the countries are venturing into these deep water and ultra deep water applications, because that is the last unexplored frontier, where we know that there is a lot of fossil fuel that is available offshore in deep waters, but with the advancements of technologies. We are getting there. We are trying to explore it now. So it's a very ongoing topic. It's very latest topic, and with every passing day, there's technology that is helping us, that is coming into the market, that is helping us to unlock and unleash these offshore reservoirs. I think this is my last slide. Thank you very much for patiently hearing.